No start it do me general. No start it do
All
me
right,
general.
sir, all right.
We just attack.
Pause it then and
Hmm?
should I pause it until class begins, sir?
Yeah, you can.
Pause the manual.
Give.
Yes, sir.
Yes, sir.
Yes, sir. And I tell you about your history, sir.
Oh. Remember that I'm not telling about the bad part, you know, just to go. Anyway, all right. Capacitance of a coaxial cable.
No, you go over this, sir.
I finished this already?
Yeah,
So
you
it
stop a
lost-
spherical capacitor.
Yes,
Oh,
sir.
yeah.
Energy stored in a copper.
Oh yeah. This one is what where we left off.
Your own paper.
Mhm. So let us read through the verbiage here to start with off. Consider a spherical capacitor formed of two concentric spherical conducting shells of radius A and B. So here we are. Radius A and radius B. This is a sphere inside a bigger sphere. Between here and here, you have a dielectric. It can be air, can be water, can be oil, whatever. The radius of the outer sphere is B, while that of the inner sphere is A. B is greater than A, which is obvious. The region between the two spheres is filled with a dielectric of permittivity epsilon. The inner sphere is given a positive charge, plus Q. You have a plus Q on the inner sphere. While for the outer sphere, it is minus Q. So the equivalent charge is on either one with opposite charge. Considering the Gaussian surface as a sphere of radius R. So R is arbitrary. Now, from the point charge there, from the point charge there, E equal 4Q over 4 pi R square AR watt-meters. Right? Look at it this way. Your inner sphere could be a point charge. Right? So the fact that it gets a little bigger doesn't change your law. Now, the potential difference is work done in moving a unit positive charge against the direction of the field from R equal B to R equal A. So V equal minus the integral of E dot dl. This is E. E is the distance between A and B. So the differential distance between A and B is dr in the AR direction. Follow that?
Oh, yeah, yes, sir.
DL, which is the distance between A and B. Right? Remember, both A and B is measured in the AR direction.
Sir, could you go back to the diagram so I can?
Yeah, just let me try to get rid of this car. Just a minute. So this is A, this is B. But both A and B are in the R direction, radially outwards. So DL, the distance between here and here, is dr AR. dr,
Okay.
which is differential length, and AR is the direction. So I'm saying that E dot DL, because this is E dot DL. DL is R, is dr AR. Right?
All right.
Yes, sir.
So if you do the like vector algebra, yeah, AR dot AR is what?
One, two.
One, right? So all this collapse to just dr. And when you finish this integral here, you get this. Which is this. Which is this. So Q equals CV. You have V now. You have Q. So you Q over V. You end up with this. Flip this up there. Cancel this. You end up with this.
Oh, yes, sir. The transposition.
And to clarify, sir, B is the outer radius and A is the inner radius.
Right. So this is the capacitance of concentric capacitor. Energy stored in a capacitor. And I'm moving quickly because I don't want to come back to this next week. I just want to. It is seen that capacitor can store the energy. Let us find the expression for the energy stored in a capacitor. Consider the simplest one of them all, which is a parallel plate capacitor as shown in the figure. You have a parallel plate capacitor, positive charge on one plate, negative charge on the other plate. So you put a voltage across the plates. So AN will be your direction normal to the plate. E equal V. Equal V over D, AN. And the energy stored is given by this, which we went
So
through.
what did you say A was again, sir? The direction normal to the plates?
AN.
Here. In.
AN is the direction normal to the plate. The energy stored is given by this, which we went over last week. And now we are just going to work the math for D and E for a parallel plate capacitor. We know that D is epsilon E, and E dot E, which is this, is nothing more than E squared. Right? Well, here we have E equal V over D. So we put this in for this, get this, and we put in this for E, we get this. Volume equal A cross D, put that in, and we end up with this. So,
So, sir,
hmm?
sir,
Hmm?
you're going to give us the value of the constants, right, sir?
Say what?
You're going to give us the value of the constants.
Yeah,
of
man.
the permittivity.
Yeah, man. Mhm. Well, you're gonna get the constant like the permittivity of free space, which would be epsilon naught. And then you know epsilon is equal to epsilon R times epsilon naught. So energy stored in a capacitor, WE, is half CV squared joules.
Yes, sir. We're not go over that all, sir.
Hmm?
We're not do this energy density.
Yeah, man. Just was trying to see how much more we have to do.
Wait, sir, what's this above the energy density, sir?
Hmm?
What's that above the energy density again?
The energy stored.
Oh, the W. Oh, no, I just need to get right on that. That's fine. No, you can go back a bit more, sir. It's just the last part, we never get. Yeah,
Get it?
yeah, I made it, sir.
No, I'm not sorry. Yeah, go there.
Oh, yo, your mic.
All right. So the last thing is the energy density. That's pretty much a self-explanatory. Tell me,
What is it, sir?
this is pretty much self-explanatory. Energy store is half that. And we just put in, just do integral. And make the substitution for D.
Sir, the D is
Energy density.
energy density. Oh
Is
yeah,
it, sir?
yeah, electric field.
Electric
Yeah.
field intensity. Mhm.
Wait, so what's W is energy stored?
Sir, are we still discussing capacitors only, or is it just general potential energy? Potential.
Capacitor.
Okay.
So then, that completes our thing on electrostatics. All right.
Sir, a question about energy stored in a electric field.
Mm.
Could you say that if you found the force of the charges and just multiply by the at the distance, some distance, you would get the energy stored in the electric field?
Not sure, understand what you.
I mean, like if you have 2-point charges and you want to try to find the energy stored in the electric field, like of
But there wouldn't be any energy stored in that electric field. If you have 2-point charges, they would be interacting with one another, right? So one would be exerting a force on the other.
oh, yes.
You with me?
All right. Sir.
All right.
Okay, so it wouldn't the depending on the distance between them if
Yeah, the force would be either greater or smaller. It'd be like two magnets, right?
Hello? Hello?
Yeah. But why do people gonna turn off their phone when them when they call it multiplex or multitask? And people that work and turn on them phone and so they log in, but they're not really here. Anyway, that's it for electrostatics. So what we're gonna do next week, we're gonna jump out and